pyridine. Okay, so pyridine is a basic heterocycle. It's a basic heterocycle. Okay, with the chemical formula of C5H5N. So what happens over here? One of your carbon and hydrogen in your benzene ring is replaced by your nitrogen. Okay, it was discovered by Scottish scientist Thomas Anderson as one of the constituent in bone oil. So this was something basic introduction. Now let's go to the uses. Uses, it is one of the basic moiety backbone in most of your compounds. It, so pyridine is used for precursor for agrochemicals, pharmaceuticals, and also as used as a solvent. As a reagent, it is used as a base, it's used as a solvent. Pyridine is added to ethanol to make it unsuitable for drinking. Yeah, so it is added to because it is poisonous. So to make it unusable, they add a bit of pyridine. It is used in the in vitro synthesis of DNA, in the synthesis of sulfapyridine, that is a drug against antibacterial, antiviral infection, antihistaminics like triphenylamine, mepramine, as well as water repellents, bactericide, and herbicide. So it has got a wide variety of its presence in both agro, pharmaceuticals, and as a bioprecursor also. Many bioprecursor contains is pyridine moiety. So some of the nomenclature. So how do you give a nomenclature for pyridine? So pyridine, the nitrogen is considered as 1. Then you go according to the numbering. So now in this case, the first example, the bromo is at the 4th position. That's why it is called 4-bromopyridine. Now in case of 2 dash 2 comma 2 dash hyphen by pyridine. So what is this? So this is a 2 pyridine because there is substitution at the second, and the second pyridine also, it's a substitution at the second pyridine. That is why it is called as 2,2 dash by pyridine. Next is 2,6-dicarboxylic or dipiccolinic acid. And next is your general formula for your pyridinium salts. So they form pyridinium salts, quaternary salts of ammonia. So they are known as pyridinium. Any positive charge where the lone pair of your nitrogens are used in your bond formation, forming coordinate bond, it is known as pyridinium cation. Okay, pyridinium cation. And this is the following resonance structure. So the lone pair, okay, the bond comes to your nitrogen, and so in this case the bond comes. So this is one of the method. The positive charge is on the, basically nitrogen can't take, it is said that being electronegative, it cannot take positive charge. So that's why it always prefers to have a negative charge on it. Okay, so the positive charge will be 2, 4, and 6. So these are the resonance structures. See, the bond between 2 and 3 comes to the nitrogen. Again, there is a shifting of bond between 3 and 4 comes between 1 and 2. Sorry, 2 and 3. So this is the resonating structure of your pyridine. Now, the structure. So what all things? As it's a cyclic, planar, conjugated double bond. It's a cyclic, planar, conjugated double bond. There is an sp2 hybridized orbital which are all on the same plane. There is a carbon-carbon single bond. There are 1, 2, 3, 4. There are 4 carbon-carbon single bonds, and that is sp sigma bonds, and there is 2 carbon-nitrogen sigma bonds. All are in same plane. Okay, and the p orbitals are perpendicular to this sp2 hybridized. The unhybridized p orbitals are at perpendicular to this plane, and this are adjacent to each other. So there is a delocalization of your electrons. There are delocalization of your electrons, and in this case, okay, okay, the lone pair of electrons, are not in of your nitrogen are not involved in your pi bond formation. It is free. The lone pair of electrons of your nitrogen is free. Okay, that's why. Okay, that's why it is basic in nature. The lone pair is not involved in your bond formation. Okay, the lone pair of electron is not involved in your bond formation. That's why it is available. As well in other cases of your 5-membered ring, the lone pair of electrons was involved in your bond formation. Okay, aromatization. Now let's go for the synthesis of your pyridine. Very much important. First is Chichi-Babin synthesis. First is Chichi-Babin synthesis. It's a reaction between an acetaldehyde with formaldehyde in presence of ammonia to give pyridine. So what is the reaction? The reaction between acetaldehyde and formaldehyde. So when acetaldehyde and formaldehyde reacts, so what is that? It's an cross Dalton condensation. It's a cross Dalton. You get an acrolein. You get an acrolein, that is CHO C double bond vinyl. Okay, that's the acrolein moiety. Now this acrolein moiety reacts with another molecule of your acetaldehyde and ammonia. So in presence of acetaldehyde and ammonia, it undergoes condensation to give you your pyridine. It undergoes condensation, okay, to give you your pyridine. Okay, so this is the first method. That is Chichi-Babin reaction. That is acetaldehyde reacts with formaldehyde first in presence of ammonia to give you pyridine. The first step is formation of acrolein. The acrolein form then reacts with your condenses with your acetaldehyde and ammonia to give you pyridine. So this is the first method, Chichi-Babin's reaction. Other methods are, see, like you take acetylene, you treat it with hydrogen cyanide, HCN. Okay, you acetylene, you take 2 moles of acetylenes and 1 mole of hydrogen cyanide. You heat it on a red hot tube, high temperature. It undergoes fuses condensation to give your pyridine. Next method is your dehydrogenation of piperidine. Piperidine is nothing but a saturated ring. So when it undergoes dehydrogenation, that is oxidation in presence of concentrated sulfuric acid at high temperature, it will give you pyridine. So your piperidine undergoes dehydrogenation in presence of concentrated H2SO4 at 300 degrees Celsius to give you your pyridine. Next is your ring enlargement. You might have studied it in your pyrrole. So when pyrrole is treated with methylene dichloride and sodium ethoxide, it undergoes ring expansion to give you your pyridine. Okay, when you heat your pyrrole with methylene chloride in presence of sodium ethoxide, it undergoes ring expansion reaction. So you get your pyridine. Okay. Next is oxidation of your beta picolin with potassium carbonate. What the first thing is, your methyl group gets oxidized to carboxylic acid, that you get your nicotinic acid, and this when you heat it calcium oxide. Okay, that means at high temperature it undergoes decarboxylation to give you your pyridine. So this is the fourth method. Next is glutonic aldehyde. So it undergoes tautomerism. Okay, it undergoes tautomerism, and when you treat it with your ammonia, when you heat it with your ammonia, you get your pyridine. So you take glutonic aldehyde with ammonia. First is tautomerism, followed by condensation with your nitrogen, that is ammonia, to give your pyridine. Other is you take tetrahedral furfural alcohol. Okay, tetrahedral furfural alcohol, you treat it with ammonia in presence of aluminum oxide at high temperature around 300 degrees Celsius. You get your pyridine. You take tetrahydrofurfural alcohol, you treat it with ammonia and in presence of aluminum oxide at 300 degrees Celsius, you heat it, you get your pyridine. That is a commercial method. Okay, the second commercial method is when you treat your acetylene in presence of ammonia and dimethyl acetal. You get in presence of aluminum oxide at 500 degrees Celsius, you get your pyridine. This is the seventh method. Then it is Haas equation, Haas pyridine synthesis. So what is this Haas pyridine synthesis? So you take, it's the first step is novel synthesis, condensation between beta keto ester and aldehyde and an aldehyde, you get an unsaturated carbonyl compound. Okay, first step is formation of your so what is the Haas equation? First is Novengel synthesis, active methylene group, so it undergoes dehydration to give you a unsaturated carbonyl compound. Second step is formation of an imine, so your ester, okay, will react with ammonia to form an enamine ester. It forms an enamine ester. See, the first step is formation. See, this thing is generation of new attack on your aldehyde, so it will form an unsaturated carbonyl compound. That's the first step. Okay, second step is your formation of your ester enamine. So your ester, beta keto ester, will react with amine to form an enamine. Okay, it undergoes tautomerism similarly to give your enamine. That is the second step. Now let's go for the third step. The third step is formation of your dihydropyridine. So what happens? The first two reactants will condense by Michael's addition. So they will condense by Michael. What happens? Your double bond attacks on your double bond of your. So if your enamine, in the case of enamine, the nitrogen gives its lone pair. So the double bond of the enamine attacks on the double bond of your unsaturated ketone. Okay, the bond from that shifts to and you get your O minus. Okay, so you got NH2 and O minus. So it undergoes tautomerism. It undergoes tautomerism. You get your NH2 double bond, and again your H gets transferred. You get your carbonyl compound. You get your amino double imine and a carbonyl compound. Okay. Now next is nucleophilic attack of your amine on your carbonyl group. Next is nucleophilic attack of your amine on your carbonyl group. So there is an OH, and the last step is your dehydration, and you get your dihydropyridine moiety. You get a dihydropyridine. This is very much important in your preparation of your calcium channel blocker, that is nifedipine. Your nifedipines can be prepared by this. Okay, this is an method for preparation of your nifedipine, that is an anti-hypertensive or anti-arrhythmic drug. It's a calcium channel blocker. So this is used in the preparation of your calcium channel blocker, that is nifedipine. So what is the first step? First step is formation of unsaturated carbonyl compound. Second step, that same beta keto esters reacts with ammonia to form an enamine. Now that next two is the condensation. Okay, condensation between the two intermediates, first two intermediates, by Michael addition. So the nitrogen comes over lone pair, attack on the unsaturated O minus positive. Then next step is tautomerism. You get your tautomers are formed. The lone pair. So the this is a tautomer is formed. Then next is your nucleophilic attack followed by dehydration. Very important, asked in your exam separately. Okay, Haas pyridine synthesis. Haas pyridine. This is one of the method. And the last step is your oxidation with DDQ. This dihydropyridine, okay, which is formed when you treat it with DDQ, that is a oxidizing agent. It removes your hydrogen and you get your aromatization. You get your aromatic pyridine ring. So this is your last step. If you want to convert it into pyridine final molecule, then you have to treat it with DDQ. That is oxidation takes place and you get your substituted pyridine. You get your substituted pyridine. Now let's go for the properties. As we know that there are 5 carbons, 1 nitrogen, and all are sp2 hybridized, and sp2 hybridized are planar. It makes a planar pyridine structure. Each ring atom contains unhybridized p orbital which is perpendicular to the plane of sigma bonds. So you got all the sp2 hybridized orbital, and the unhybridized p orbital is perpendicular to the plane of sigma bond, and the p orbitals are parallel to each other, and you know they are next to each other. Okay, so overlapping between p orbitals are possible, similar to that of your benzene. There are total number of bonding electrons are 6, that is 5 from your the 5 from your carbon and 1 from your nitrogen. So and the resonance, this favors your Huckel's rule. So there are 6, that is 2 and 4 and plus 2 electrons, that is 1, you get 6. So there are 6 non-bonding electrons, and thus they favor your Huckel's rule. That's the reason why your pyridine is aromatic, because it has planar, it is conjugated, it has 4 and plus 2 pi electron, that is 6 non-bonding electrons. So this is how pyridine is aromatic in nature. That's the first property, that it is aromatic. Basicity. Now let's compare some basicity of pyridine. These are almost 2 marks questions that you get. Pyridine is more basic than pyrrole. Why pyridine is more? In this case, in case of pyridine, the lone pair of electrons is free, and basicity depends upon the availability of your lone pair. Whereas in case of pyrrole, this lone pair of electron is involved in your aromaticity. So in order to get 4 and plus 2 pi pi electrons, you should have your pyridine's your pyrrole's lone pair is involved in your ring stabilization. So that's why it is weakly based. Whereas in case of pyridine, you can see the lone pair of electron is free to be available. That's the reason why your pyridine is more basic than your pyrrole. So the most important thing for the basicity is availability of your lone pair of electrons. So in case of pyridine, the lone pair of electron is available. Whereas in case of pyrrole, the lone pair of electron is not available. That's why it is weakly basic than that of your pyridine. Okay, this is about the basicity of pyridine. So it reacts with your HCl to form pyridinium hydrochloride. Okay, because the lone pair of electrons will be given, and it forms a pyridinium hydrochloride salt. Okay, now there is one more thing. These are some of the basics that you have to know. Pyridine is less basic than your aliphatic amine. Why? Because your sp2 hybridization, as the S characters uh, increases. So what happens? As the S character increases, the electropositivity increases. Okay, and as the S character increases in sp2 hybridized, N is more electronegative, that is more S character than your sp3 hybridized lone pair electrons. So it is closely held towards the electronegativity. The electrons are closely held towards, because as the S character increases, the electronegativity increases. So in case of sp2, the S character is more. Okay, that's why they are, in case of sp2 hybridized, they are loosely bound, so they are less available for acid base reaction. The lone pair of electrons are not available in pyridine, so it is less basic than your aliphatic amine. So your S character plays an important role in your basicity. So more electronegative, more boundly, so it is less available. Tautomerism. So what is this tautomerism? Tautomeric structures involved with pyridine substituted at the 2 and 4 position. So if there is any substitution at the 2 and 4, but this is very important to be known whenever you do a reaction. So if there is any group which can tautomerize, okay, with the lone pair of electron at the 4th or the 2nd or 4th position, so it will tautomerize, like sodium, nitrogen and sulfur. If there is such groups with the lone pair, they can tautomerize. So 2-hydroxypyridine, okay, OH, and you get a pyridone. So this is an hydrogen bond donor, okay, and bond acceptor. So O minus, so that will tautomerize, because your nitrogen is a hydrogen pair donor. Okay, so you get your 2 pyridone. So this is very important, because this plays in very important in your designing of drugs. So if there is any OH, O, nitrogen or sulfur, it undergoes tautomerism. It also has it is soluble in water, because it can form an hydrogen bonding. So it can undergo solvation. That's why its solubility is better in water compared to that of your other solvents, other organic compounds. Okay, so this was some of the basic properties of your these are some of the basic properties of your pyridine. So let's the reactions one by one. So electrophilic addition on your nitrogen. Electrophilic addition, it's an addition, not substitution. It's an addition reaction. So electrophilic addition on your nitrogen, it gets protonated, as you have seen in basic property. It gets protonated to form pyridium chloride. An alkylation, when you treat it with your methyl iodide, it undergoes an alkylation to form 1 methyl pyridium iodide. So this is an electrophilic addition reaction. Something gets added, there is no substitution, there is no replacement, anything, there is just an addition. So this is known as electrophilic addition reaction. So because your methylene ion gets added over here. Now the electrophilic substitution reaction, this is very much important. Pyridine gives electrophilic reaction at the third position. The pyridine gives electrophilic substitution reaction at the third position. Why? Why does pyridine give? If you see at the second position, and when the nucleophile attacks, the positive charge moves around and comes on the positive charge comes on the nitrogen. Okay. Similarly, in case of when there is a electrophilic attack at the fourth position, similarly the nitrogen gets the positive charge. Nitrogen is electron, so a positive charge destabilizes the nitrogen structure. So if a positive charge comes on your nitrogen, it destabilizes it, and here the attacker generates positive. As you have seen, when there is an attack at second and fourth, electrophilic attack at the fourth, the positive charge comes on the nitrogen. So this is less favorable. And when you see at C3 position, when you see the attack at the C3, electrophile attacks at the C3 position, there is no positive charge on the nitrogen. The nitrogen does not get positive. That's why your electrophilic substitution reaction is favored on the third position. It's favored on the third position. It's favored on the third position. Okay. So this is the intermediate. That is, when you do the resonance structure, it is the most unfavorable position because the positive charge on the nitrogen makes it 6. It is very unfavorable. Okay, because lesser electrons, so its octet is not formed. That's why their substitution takes place at the third position. Some of the reactions of electrophilic reaction, potassium nitrate, so it requires harsh condition. All this reaction takes place at harsh condition. It requires very high degree because it is deactivating for electrophilic substitution reaction because of the presence of nitrogen in the ring. So in presence of potassium nitrate and H2SO at a high temperature, the yield is very poor. Okay, it's on high temperature, you get a 3-nitropyridine. Similarly, fuming nitric acid, fuming H2SO4 in presence of your mercuric sulfate at high temperature. Okay, mercuric sulfate is used, you get a pyridinium 3-chloride. Charcoal, even the same thing with bromination, you get 3-bromo and 3,5-dibromo. That's also high temperature, 300 degrees. You get 3-bromopyridine and 3,5-dibromopyridine. So these are some of the electrophilic substitution reaction. Now let's go for the nucleophilic. So now nucleophile is what? Negative charge. So when there is a negative charge in the ring, nitrogen being electronegative, it can take on the electrons. So whenever the addition is at the second and fourth position, okay, whenever there is addition at there is an increased charge on your negative charge. So nitrogen being electronegative can take away the electron. So addition, the nucleophilic reactions takes place at the second and the fourth position. So nucleophilic reaction takes place at the second and the fourth position without and aromaticity is gained by the loss of hydride. So what aromaticity is gained by what? By loss of hydride ion, that is H minus. Okay, aromatic in case of electrophilic reaction, it takes by the loss of proton, whereas in case of nucleophilic reaction, aromaticity is obtained by a loss of hydride ion, that is H minus. Okay, remember this thing. So takes place by the absence of your hydride ion. So this is how the most stable structures are obtained. You have to draw these structures. Okay, why? Because more stable is when there is a charge, when there is a negative charge on your nitrogen, because it can take away electron, being its electronegativity. Okay, some of the reaction: Chibabin's reaction, when pyridine reacts with sodium hydride in presence of ammonia, you heat it, it gives your pyridine 2 amine. Pyridine 2 amine. So nucleophile this N minus NH2 ion attacks on your nitrogen. There is a delocalization, negative charge comes, loss of hydride ion to get aromaticity, and you get your pyridine 2 amine. So this is your nucleophilic substitution reaction. Nucleophile means negatively charged, attacks on your pyridine ring. Okay. Some of the other examples are sodium hydroxide reacts use of 2-hydroxypyridine, which undergoes tautomerism to give 2-pyrididone. Okay. Next is N-butyl lithium. You get your 2N-butyl pyridine. Your butyl gets added at the second position. These are some of the very important reactions to be known. Nucleophilic reaction. So it undergoes oxidation in presence of peroxides. It forms pyridine N oxide. It forms pyridine N. It undergoes reduction with Raney nickel at high temperature in presence of your hydrogen. Okay, nickel to form your pyridine, reverse of your starting. As we have said, when we react with methyl bromide, alkyl bromide, it forms N-methyl pyridinium bromide. Okay, quaternary salts. It undergoes electrophilic addition reaction. So these are some of the reactions of pyridine. So some derivatives of pyridines are Piccolins. So what are these Piccolins? So your pyridine ring with substituted methyl in the ring. So if the methyl group is substituted at 2 position, it is known as 2-methyl pyridine or alpha picolin. If it is substituted at 3 position, it is known as beta picolin. Okay, and if it is substituted at the 4th position, methyl, it is known as gamma picolin. Okay, this plays a very important role in various synthetic process. Okay, so these picolins play a very important role. Okay, so what is its application? It is used for the preparation of pyridine 3 carboxylic acid or nicotinic acid. Beta picolin is used for the synthesis of your nicotinic acid. Some of the bioactive precursors, where all they are present? This is present in nicotine. Okay, so pyridine forms the base for your nicotine. Okay, this is active constituent of and toxic and addictive in nature. It is also as a major part of your sulfapyridine. Sulfapyridine is a sulfonamide antibacterial agent. It is the oldest of your antibiotics. Paraquat is one of the oldest herbicide. So it is an N-methyl pyridinium salt, N-methyl pyridinium salt. Isoniazid is one of the most commonly cheapest antitubercular drug. Okay, it is an commonest. Isoniazid is the commonest of your anti-TB drug. It is nicotinic isonicotinic hydrazide. That is, it contains an hydrazide at your 4th position. Okay, so that are some of the bioactive pyridine. So these are some of the medicinal use of some other drugs, sulfapyridine, which I have mentioned. Anticholinesterase pyridostigmine, so which is used in myasthenia gravis,